Homogeneity is often ignored in data analysis, but it matters more than almost anything else. Recognizing its importance is the key to meaningful statistical conclusions. Before asking about normality, sample size, or p-values, there is a more fundamental question most analysts never consider. Is this data homogeneous? Donald Wheeler emphasizes that homogeneity is the gatekeeper assumption. If you get it wrong, all subsequent analysis becomes unreliable. Homogeneity does not mean all values are identical or that the data shows low variation. It means there is one consistent process generating the data, with one operating condition and one mechanism of variation. The data may vary, but the reason for variation must remain consistent. Combining data from different sources creates artificial patterns that do not represent any real system. Descriptive statistics assume homogeneity, so we start with averages and standard deviations. Classical tools rely on the data coming from a stable, homogeneous process. Mixing data from different conditions creates an undefined blend. Skip the question of homogeneity, and every other answer will be wrong. Statistical inference assumes your sample comes from one unique dataset. If data come from multiple sources, your interval estimate becomes meaningless. Before using inference methods, we must examine data for evidence of homogeneity. Mixing apples and oranges to describe the average fruit creates meaningless results. Your standard deviation becomes inflated, your capability index misleading, your probability model wrong, and your confidence interval describes nothing. Without homogeneity, we are analyzing many processes mixed together, not one. Textbooks use controlled experiments with homogeneous conditions. In real operations, we face different operators, materials, and environmental conditions. Most operational and business data are observational and often contain hidden changes or assignable causes. Without removing these, we are mixing multiple processes. Software assumes homogeneity by default, never flagging mixed populations. Results look rigorous and credible, but tools fit regression lines and produce statistics without checking if data belong together. Professional output creates false confidence, discouraging users from questioning assumptions. Pooling data feels rigorous, providing more points and smaller p-values. However, more data from different processes produces confusion, not knowledge. Large mixed datasets obscure structural problems, and Wheeler's research shows that fewer observations from a single process are more reliable than a large mixed set. Processes drift, operators change, materials switch, tools wear, and undocumented adjustments happen. Each change creates a new system of causes, a new population. Treating concatenated data as homogeneous produces summaries that don't represent any actual process state. Homogeneity cannot be determined from a histogram alone, because histograms remove time order and causality. Attractive distributions may combine incompatible realities. Wheeler insists on process behavior charts as the primary tool for assessing homogeneity, because time-ordered charts reveal shifts, trends, and cycles hidden by histograms. A stable process equals homogeneous data. Unstable signals indicate mixed populations. Predictability is established through time-ordered analysis. If process behavior charts show consistent variation in center, summarizing data makes sense. Otherwise, the data are not homogeneous and must be separated first. Mixing development and production data inflates variation and drives conservative requirements. Pooled data creates artificial outliers and missignals, and regulatory risk increases when traceability is undermined in regulated environments. A process can be non-normal and still perfectly analyzable if the data are homogeneous. The critical requirement is consistency of the generating mechanism, not conformity to a mathematical distribution. Homogeneity addresses whether the same system produced all numbers, while normality is often irrelevant. Wheeler criticizes premature data transformation and normality testing before homogeneity. Homogeneity cannot be automated or outsourced. It requires process knowledge, human judgment, and context. No definitive numerical test exists. Wheeler argues that this discomfort with judgment is valuable. It forces analysts to engage with the actual process rather than treating numbers as abstract objects. A process has one consistent voice. Multiple voices indicate mixed sources, creating confusion. Wheeler urges listening to the process before analyzing. Homogeneity means listening to what the process says before speaking statistically about its behavior. Maintain chronological sequence in data collection. Create process behavior charts and plot data with time on the horizontal axis. Assess stability. Look for shifts, trends, cycles, and outliers, and separate distinct regimes. Document context and record operating conditions and changes. Protocols must preserve time order as essential information. Before averages, regression, capability analysis, or prediction, establish homogeneity. It is not a minor detail. It is the foundation of trustworthy analysis. Wheeler teaches us to replace reflexive statistical testing with thoughtful process understanding and time-ordered analysis. The goal is conscious awareness of when data belong together, enabling appropriate analytical responses.